So far we have covered a lot of ground in propositional logic. We have given lots of definitions and notations and looked at a bunch of examples of the theory side of propositional logic. And while in the very beginning of the video I gave you some motivations about why you as a computer scientist should care about propositional logic, what I'd like to do now is transition to some actual practical examples and applications of the theoretical groundwork that we have laid so far. And in particular, what I want to do is cover translation of English sentences into propositional logic. Secondly, I want to talk about system specification and how that relates to propositional logic. And third, I want to talk about logic circuits. But unfortunately, before we get to the fun applications, there are just two remaining items that we need to cover more in the theory realm of propositional logic. In particular, we need to cover order of operations, and secondly, we need to cover the definition of tautology and contradiction. So very briefly, let's go ahead and cover these concepts. So order of operations. You might recall back from like grade school that statements such as this would be ambiguous if we didn't have some sort of convention about which one of these operators we apply first. We have a plus and we have a multiply right here. And in fact, you can still to this day see memes go around or Facebook posts or stuff like that that confuse people because they don't recall from grade school the proper order of operations. And so we have some convention about when to apply these different operators of plus and multiply so that statements like this are not ambiguous. So it's a convention that we use so that we don't make ambiguous statements. So in particular right here, of course, we recall that the multiplication trumps the addition, and so we're going to do the multiplication first before we do the addition. So similarly, there is an order of operations when it comes to propositional logic. So in particular, we have our operators, and we also have our precedence of the operators. Basically, which one of these should you apply first? So of the propositional logic operators that we have introduced so far, here is the following list. So not trumps everything. So it has precedence 1. It is first priority. That is the first thing that you are going to apply, is the not symbol. Next after that, and, or, and zor. And, or, and zor come next. And they are the next in the precedence list right here, number 2. And lastly, conditional and biconditional, or implication and by implication is the very last one right here. So this is the order in which you will apply these operators. So similarly, how in this particular example, multiplication has a higher precedence. That means we do it first, and then addition. It's a similar thing for this list right here. So as an example, if we were to write some proposition that looked like the following: not P and Q implies R XOR not S. We need to know in what order we're going to apply these. So utilizing our precedence of operators right here, I'm going to use brackets to represent when we apply the different operations here. So once again, the not trumps everything. So in particular, this not P right here, that would be the very first thing that we would look at. And this not S over here also has top priority. And after that comes the ands, ors, and zors. So we would have the and Q right here, and that would be evaluated next. And we have this zor right here and an R, and that would be evaluated next right here. And on the lowest of the precedence table right here, we have our implication. So these brackets right here demonstrate the order in which you would evaluate these things. You would do the nots first, then the ands, ors, zors, and then after that, our implication. And so basically this right here is simply a convention. So this is a convention. That way we don't have to write a ton of brackets. Because I don't know about you, but I'd get really bored of writing all these brackets all the time. And it's a whole lot easier just to remember this convention of order of operations rather than having to write 7 million brackets over here. By the way, this particular part of order of operations is covered in Rosen 1.1.5 if you want to reference this material and see a few more examples of this. Now, the next thing that we're going to look at is tautology and contradiction, the last thing that we have to define before we can move on to our practical applications. So this particular definition right here is contained in Rosen 1.3.1. Side note, it's kind of interesting the way Rosen orders some of his stuff. In fact, he actually uses some definitions before he actually defines them. So that explains why you might see me jumping around from different sections, because I like to give the definitions of things before I actually use them in practice. So let's go ahead and look at tautology and contradiction. As I mentioned, these are definitions. So we are going to define, first off, a tautology. So a compound statement is a tautology. Tautology right there, if it takes on the truth value of true, no matter the value of its underlying variables. So that compound statement is always true. And the next definition, in fact, it's basically the same but flipped. So let's go ahead and see if we can write this out really quickly. So a compound statement is a contradiction if it takes on the truth value of false, no matter the value of its underlying variables. So basically the only difference between these two is it's a tautology if it's always true, and it's a contradiction if it's always false. So let's go ahead and look at a couple of examples of these. So for example, we could consider the following logical proposition: P and not P. P and not P, a perfectly fine compound statement right here. It only contains one underlying variable, P right here. So let's go ahead and look at its truth table and see what we get. So here, there's only one underlying variable, that's a P. And so its truth table is going to be nice and simple. Its truth table could be true or false for that value of P right here. And so, recalling our order of operations right here, this not is the very first thing that we apply. And so, true, we flip it, it becomes a false. Well, this then will become a false and a true. A false and a true is going to be false right here. In the second row, well, false and anything is going to be false because we know the definition of and requires them both to be true. So this one again is going to be false. So in particular, no matter the value of its underlying variables right here, this thing is always false. And so in particular, this thing right here is a contradiction. P and not P is a contradiction. It will never be true. It is always false. So here, I need to consider the statement P or not P. It's very closely related. All I've done is flip the and to an or right here. Once again, this compound proposition has only a single underlying variable, so its truth table is going to be simple. Since I'm running out of space, that's why I picked such a small example right here. So again, writing out its truth table, we get, write down all of the possible values of its underlying variables, and let's go ahead and figure this out. This or right here only needs one side or the other to be true, so we already know that this first row here is going to be a true. And in the last row right here, well, the first one is false, but the second one right here, it flips it, so the false becomes a true, and so it's a false or true, which is also a true statement right here. So because of that, this right here is indeed a tautology. No matter the values of its underlying variables, this compound proposition right here is always going to be true.